AP Chemistry, and welcome to section 16.9 covering salts, where we kind of take the entire discussion we've had all chapter about conjugate pairs, weak acids, weak bases, and turn it into a very, very thoughtful analysis of salts, where what do we mean by salts? Right, we mean an ionic compound. So let's talk about a couple of basics first, right? We talked about how an acid, right, plus water can dissociate or equilibrate to form H3O plus and A minus. Yes? We talked about how bases will react with water via hydrolysis to form a protonated base plus hydroxide ion. Yes? All that's clear? All right. So then it turns out, like we've been talking about over the course of this chapter, right? Like we talked about here, right? If something is an acid, right, its conjugate base will have a Kb value, right? Acid, conjugate base. All of these bases have Kb values. Some of them are pretty basic, right? Which means that, if we think about what that means, this has the capability of acting as a base, right? So here's my acid, first of all. Here's its conjugate base, which means that anions, right, of a salt can be thought of as the conjugate base of an acid. Yes? The anion of a salt can be thought of as the conjugate base of an acid. Yes? All right. Likewise, cations can be thought of as the conjugate what? Right, the conjugate acid from a base. Yes? All right. Which means that anytime we have a salt, it's going to be composed of a cation and an anion, and we need to think about, right, where those species come from, right? So, for example, if I have a compound like NaCl, for example, right? Let's talk about analyzing my anion, right? So chloride ion, right, comes from the conjugate base of an acid, right? Is the conjugate base of what acid? Right, is the conjugate base of hydrochloric acid, which is a strong acid. Now, the conjugate base of a strong acid, going back to what we talked about at the very beginning of the chapter, the conjugate base of a strong acid is negligible in terms of its basicity. Negligible, right? Which means that it has no tendency to act as a base. Chloride ion has no tendency to reform HCl and hydroxide. Yes? Does that make sense? Right? Because if this were going to react with water and form HCl, what would happen? Right, it would dissociate, form hydronium ion, which would then neutralize all of this if it were to happen, which is why this negligible as far as the base goes and no impact on our pH. Yes? So, by extension, what we can say is that the conjugate base of a strong acid has no impact on pH. The conjugate base of a strong acid has no impact on pH. Okay? All right, moving on to our cation, right? So here we have Na+, which if we think about that as being the conjugate acid of something, right? What would that be the conjugate acid of? Right. That would actually be the conjugate acid of sodium hydroxide, right? That's the base that would come from, right? This is a strong base, right? Which means that sodium ion has no tendency in water to form NaOH, right? And H+, right? That's not something that it's going to do, right? Because this would dissociate, forming hydroxide ions, which would then neutralize these, leaving us with a neutral solution, right? Which means that sodium ion has no tendency to produce hydronium, which means that it has no effect on pH. So by extension, conjugate acids from strong bases have no effect on pH. Conjugate acids from strong bases have no effect on pH. Okay? Now, Then that brings us to the whole other category of things, the weak species, right? So let's say instead that we have NH4. So what's this? Ammonium acetate, right? Whereas here, right, C2H3O2, right, thinking here, again, so this is my anion component, right? My anion is going to be the conjugate base of, right, I don't know why that would go there. So it's going to come from acetic acid, which is what kind of acid? Weak acid, right? Which means that this compound actually does have some tendency in water. Nope, that's not what I mean. To do this, yes? This has some tendency to do that because we know that this doesn't dissociate, right? So when this reacts with this, we do get the buildup of some of this, which means we get the buildup of some of this, which means that in this case, this does have an effect on pH, right? So that means that the conjugate base of a weak acid, does exhibit basic tendencies. Or we could say that the conjugate base of a weak acid acts as a weak base, right? Now, we would not say that this is a strong base, right? We would not say that this is on par with sodium hydroxide, for example, right? But it does act like a base, so we would say that it is basic, right? Weak base, right? Here we have the ammonium ion, right? So ammonium, right, comes from, right, so again, these come from our acids. These are the conjugate bases of acids, right? This is the conjugate acid of a base, right? And again, going by definitions, right? Conjugate acid means the protonated form. So this is the protonated form of this, right? This is a weak base, meaning that this does have a tendency with water, right, to do this, right? This has the tendency to act as an acid, producing hydronium ion in water and raising the pH of our solution. Yes? So we could also say that the conjugate acid of a weak base is weakly acidic and will affect our pH, right? The conjugate acid of a weak base acts as a weak acid and will increase the pH of our solution. Yes? All right. This is probably one of the hardest parts of the chapter, okay? Because we're taking all those little tidbits that we've committed to memory, and if they're not committed to memory really, really well, this analysis breaks down, right? And this analysis, the ability to analyze salts, the ability to analyze a cation and an anion independently and what they're going to do with water, is really what makes up the bulk of our Chapter 17 discussion, where we talk about buffers and how they work, right? So make sure you look this over, make sure this makes sense, and if it doesn't, you need to be spending time with me until it does. All right. Another exception sort of, or something that is a little bit more thoughtful, right, are small highly charged cations, right, like iron and aluminum, those being some of the most common examples, right, wherein they form complex ions, right? We actually saw this with our cobalt in solution also, where we said the cobalt forms a complex ion with water, right? And so what that kind of does, right, is that this is my iron plus 3 here, right? And then iron basically is strongly attracted to water molecules, right? Specifically the negative ends of my water molecules, which means that, right, the electron density is sort of pulled in this direction, which means that this bond is a little bit weaker than it would be otherwise, because the electron density, right, is being pulled in this direction, right? And anytime the electron density is pulled further from my hydrogen, it makes that hydrogen easier to take away. Yes, anytime we pull electron density away, that hydrogen is easier to take, which means that these lone pairs of water can go ahead and take that proton, leaving us with a hydronium ion in solution, right? Meaning that small, highly charged cations are acidic in nature, okay? We don't do a whole bunch of that, but it is something you should be familiar with. Okay, next up. All right. So looking at some solutions. So here we have solutions with indicators in them, right? So here we have a solution of sodium nitrate, calcium nitrate, zinc nitrate, and aluminum nitrate. So what do they all have in common? Right, so they all have the nitrate ion in common. Now, so they all have the same anion. So thinking back again, anions, right, meaning that they have been deprotonated, are the what? Right, conjugate bases of some acid. So this is the conjugate base of HNO3, right, which is a strong acid. Now, since HNO3 is a strong acid, its conjugate base is of negligible basicity, right? This has no tendency to abstract protons from water, increasing the hydroxide ion of our solution, yes? Which means that this, across the board, has no effect on my pH, right? Which means that we're just looking at our cations, right? So here, this is the cation from a strong base, right? No effect on pH. This is the cation from another strong base, negligible effect on pH, right? Zinc is a small, right, relatively highly charged cation, right? Aluminum, also small, even more charged, right? And which is why we get more and more acidic in terms of our pH, right? Because we get more and more of this process, right, where we abstract that proton, creating hydronium ion, okay? All right, next up. Here, we're going to do some analysis. So indicate which salt in each of the following pairs forms the more acidic or less basic 0.1 molar, 0.01 molar solution, right? More acidic, right? Let's think about what that means. More acidic means higher pH, which means more H3O+, right? So that's what we're really looking for. So thinking about that, right? Looking at our species, right? So here they have the nitrate ion in common, and we just talked about the nitrate ion as being negligible, right? So when we look here, right? Here we have an Fe3+ versus an Na+, right? This comes from a strong base, right? Therefore, no effect on pH. This small, highly charged cation, you should just commit them to memory: iron, zinc, and aluminum, cobalt to some extent. Here, small, highly charged cation, therefore, right, it tends to produce H3O+ in solution, which means this is my more acidic solution. All right, here. So they both have potassium in common, right, which means that potassium's not going to be our point of reference, okay? And if we think about potassium ions, right, they come from strong base, which means negligible effect on pH. So that leaves us with bromide versus hypobromite, okay? Now, bromide comes from, bromide is the what? Conjugate base of HBr. HBr is a strong acid, therefore negligible basicity, yes? Negligible basicity, no tendency to react with water, abstracting protons, creating hydroxide ion. Not what it does, which means this will have a pH of about 7. This one, on the other hand, hypobromite, right? BRO- is the conjugate base of what? Right. This. Now, is this a strong acid? No, this is a weak acid, which means that anytime it is the conjugate base of a weak acid, that means this does have a tendency in water to take that proton and increase the amount of hydroxide ion in solution. So if this is going to increase the hydroxide ion, this is going to have a pH of what? Right, greater than 7. Going back here, right, we are looking for more acidic, oh, this should not say higher pH, this should say lower pH. Lower pH, more H3O, so which is my answer? That's my answer. All right. So here we have these two compounds where the chloride ion is the same in both. Negligible, right? And if we think about where it comes from, right, chloride ion is the anion, anions meaning conjugate base or deprotonated form of HCl, which is a strong acid, which means no effect on pH anyway, right? So then we're comparing our other species, right? So we have our barium ion, which is the, right, conjugate acid of barium hydroxide. As the conjugate acid of a strong base, it has negligible effects on pH, which means that this one should be pretty close to 7, right? Then we have to look at this. So this says CH3 NH3. Now, if it's stuck to the chloride ion, what do we also know? Right, CH3NH3 plus, right? Now, if we look at the setup of this, right, CH3, remember that's a group, right, CH3 is stuck to the nitrogen because, again, carbon is what makes up our bone. Hydrogen doesn't make up our backbone. And then that nitrogen is then stuck to 3 other things, right, which is what gives us that positive charge. Now, I have a nitrogen stuck to 4 things, which is protonated, meaning that this is the conjugate acid of CH3 what? NH2. Yes? Where in here, it would be a nitrogen stuck to 1, 2, 3 things, which means here, it would have its lone pair. Yes? So this is the conjugate acid of a weak base, which means that this behaves weakly acidic, right? Meaning that this does have the tendency in water to go ahead and form some, I don't know why I can't write this right now, H3O plus CH3 and H2. Increasing the amount of hydronium ion, meaning increasing my, I don't know what I'm trying to say, increasing the hydronium ion, which means decreasing my pH, which means this one should have a pH of less than 7, right? Which means this is the answer I'm looking for. All right, here, finally, we have NH4, so that part's going to be common, which means that's definitely not what we're comparing. By the way, same analysis here, right? So NH4, cation, right, is going to be the cations are going to be the conjugate acids of some base, right? Meaning the deprotonated form would be NH3, all right? This is a weak base, which means that NH4 is also weakly acidic. Yes? Weakly acidic. This functions as a weak acid, which means that NH4 plus in solution has the habit of forming NH3 and hydronium ion, which means that both of these are going to be a little bit acidic based on the NH4 plus. Yes? All right, so that means we're talking about these. So nitrate, going back up here, nitrate is the anion from a strong acid, negligible in terms of effect, which means that this one is going to be due to that, which means this has a pH of less than 7. All right. Here we have the nitrite ion, right? So NO2 is going to be the what? Conjugate base of nitrous acid, which is a weak acid, which means that nitrite has the tendency in solution to form HNO2 plus hydroxide. Now, if it's producing hydroxide while the other one is producing hydronium, what does that mean about its pH? Right, means it's going to be less acidic than this. Yeah, does that make sense? You don't know how much more, right, or how much less, but less acidic than this is going to be, which means that's going to be our answer. Yes? Make sure you go back through all of this and make sure you can do this really quickly and simply. Obviously, on the multiple choice section where you're just choosing which one is more or less acidic, right, how you justify that is less important, right? And you can just stick with what you've memorized, right? Conjugate base of an acid, blah, 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 right? If it's a free response and you're asked to provide an explanation, then you do need to be able to write out these equations and discuss why it does what it does, right? So that's super duper important, right? Going back to a written explanation, right? If we're talking about something like here, right? So for example, just to highlight in a different color, here, if we're talking about this, for example, if HCl, right, going back to our discussion, right? If HCl is a strong acid, it dissociates completely, right? If it dissociates completely, even if chloride ion were to react with water to form HCl, it would dissociate completely, right? Which is why this is moot in terms of, or useless in terms of pH, affecting pH, all right? Okay, so we're going to pause here and we will pick up in the next one.